Apresentação. A ver se está. Excellent. Still me. So yeah, just to tell you about the Institut Côte d'Azur. Yeah, in fact, we say Troisia like in French, so it's like a brand. So it's Côte d'Azur. So it's one of the 4 institutes that we have in France. So interdisciplinary institutes on AI. This is why there is 3I. So we have, of course, a very important part of the work which has to be done in research. So we really have the goal to advance research in AI. But we also have okay. I'm not going to do that. We also have the mission to enhance partnership and innovation. And something that is also important for us, and already told you about that, is education. In particular, because we think that at some point, if we would like to massively advance in AI, we will have also to train more people. Because at the moment, we have only a few engineers, technicians that are trained to AI. And if we would like the companies to use the tools that we produce in research, we need to have technician, researcher, but also perhaps manager that are okay with the concept of AI. And this is something we try also to do. So in teaching, we have very technical courses, but we also have some courses to just introduce the concept and make people comfortable with the idea and the technology. So this is the goal, the different goals that we have, and for that we have some programs, and we have some fund to go in this direction, and we do that really with companies. And in fact, it's mandatory for us in the contract with the government. We need to have 1/3 of the money which is coming from the company. So it's an important commitment, but it's also very interesting because I think it's a way for companies to be involved in the project. And I think you really have the same relationship with IBM here. And here we really do the same program here. So at the moment, we have almost 140 companies which are working with us on a regular basis. Perhaps I missed something. Okay, it's another. This is what. Okay, and now I would like to present, as you did, some work we do at Troisia Côte d'Azur, some technical work. So I am the director, but also a chair of the institute, and I am, in fact, a statistician. I'm doing statistical machine learning, and I'm going to present a very short application of statistical learning to some public health problems. So just to tell you, but I think it's very clear for everyone now that, of course, AI is important, and we have different fields in AI, and of course, I am more in the statistical machine learning field. We saw very interesting and important advances thanks to machine learning in the last, let's say, 2 decades. But it's also, it's not the end of the story. There is a lot of issues that has to be taken into account in the next years, of course, because they are very important. And if you just think about the problem of high-dimensional data, the problem of streams of data, the problem of dynamic data, and also the problem of heterogeneous data, which is, in my opinion, perhaps the more difficult, and I heard this term today. We really need to advance and continue to do research also in statistical learning and machine learning. And this is what we try to do in my team. And with the focus, with also the importance of understanding. In my team, we really work a lot, in particular with medical doctors. And of course, for them, but it's true for a lot of application fields. Okay, using a very efficient method is a good idea, but if we do not understand the results, it's a problem, because if I have to explain to a patient why I made this decision as a medical doctor, of course, it's more comfortable for me to have this kind of information. So yeah, just to tell you that I have a team, which is a joint team between INRIA and Université Côte d'Azur. It's called the Maasai, for Model and Algorithm for Artificial Intelligence. And as you see, we are really trying to develop the next models and algorithms for AI. And we mainly work either on the theory of deep learning, unsupervised learning, adaptive and robust learning, but also heterogeneous and complex data, always with the idea of applications. So it's very important for us to not do that only on the theoretical side, but okay, try to apply and show that it's useful. And we do that for graphs, for function data, images, etc. And I would like to present just two examples of what I am doing with my team. The first one is really a theoretical problem that inspired by a real problem. In fact, it's a problem of pharmacovigilance. Pharmacovigilance, it's a public health discipline, which is, of course, important, is the study of the interaction of drugs with the adversarial issues that we have. And of course, we heard a lot about pharmacovigilance in the last years for the COVID vaccine, for instance. Okay, and it's a really complex situation, because at least in France, it's quite well organized, but patients have to declare on some website the adverse effects that they observed. And most of the time, there is a big noise which is generated by the TV shows, the media, etc. And this is the case in particular for COVID vaccine, because we were so anxious about this that people reported massively adversarial effects that are known. So it's not interesting for pharmacovigilance. So there is this very big problem of finding, weak signals in a lot of data that are finally noise. So it's really a problem. So here we work with the hospital of Nice, and we have this kind of data. So here you have the adversarial effect, and here you have the name of the drug. And every time we have someone reporting the data, we have a point here. And this is, of course, a dynamic source of data, because here we work on data for 10 years. Okay. And when you have this kind of massive data, so just to imagine that this is just a part of the data, because we have about 600 drugs that are interesting to follow, and also 700 adversarial effects. So it's quite a big matrix, and you observe it every second, every minute, every month, if you want. It's really a dynamic source of data. So,
do you use one of these general vocabularies for diagnostic?
No. Here it's a really a form where the patient say the drug, the name of the drug, and then the type of adversarial effect, and there is a medical doctor that puts the data in the matrix. So we don't have at the moment any problem of that, but of course it would be great if we like to extract to use more data, more weak data to have.
Standards like Medra.
This here is at least in France it's organized with a specific format. I don't know all the detail about this. So the data we have are like this. So big matrices of count data. So every entry of the matrix is a number of declaration of interaction between this drug and this adversarial effect. And we have a lot of matrices. And we would like to provide the medical doctors a summary of the data. And to summarize those massive data, we propose to do what we call co-clustering. So we will cluster the drugs, cluster the adversarial effect, but also cluster the time. So in order perhaps to detect some big change in the data structure. So I'm not going to, so the model is one slide, so there is some equation, but don't worry. So for that, so it's a statistical model. We assume some latent variable, random variable. So Zi will be the cluster of the drug I. Wj will be the cluster of the adversarial effect J. And we assume some multinomial distribution for this. We also cluster the time instance in the spirit that we expect to have some periods of time where the system is stable. And at some point, I don't know, because there is a big pandemic, for instance, we enter another period which is again stable before to come back to another period. And we really model like this. So here it's just an example of some clusters of time. So here you have a very intense period with a lot of declaration, something which is average. Here, very flat period, no declaration, and we come back to some very intermediate, very active, etc. So we have this kind of clustering of the time, which is great to understand afterward the dynamic. And here again, we introduce a latent variable to cluster the time. And when you have the knowledge of this, we don't have, but let's suppose for the moment we have it, you can then define a block conditional density function for the data. And here, because it's count data, we assume a Poisson distribution. And when you create this, it's a modeling with a non-homogeneous Poisson mixture model. So of course, this is a model, it's an easy part, and but we don't know Z, we don't know W, we don't know S, we don't know gamma, rho, delta, and we don't know lambda. So there's a lot of things to infer from data. So this is an easy part. This is just a summary of the model. And of course, what is difficult is write an algorithm which is able to, from the data, recover all this information. So I'm not going to enter into detail, but we use a stochastic acceptation maximization algorithm, which help us to recover all this information only from the data. So it's quite impressive because in green, you have the only source of observed data, and we would like to recover all the other parameters only from the green part. So it's, of course, an easy task of defining the model, more difficult to inferring the model from data. So this is just a table to show you that it's working, so just trust me. Something important as well, and here I didn't define the notion of clusters and the number of clusters in particular. We also have an algorithm, let's say a criterion, that is able to automatically recover the actual number of cluster of drugs, cluster of adversarial effect, and cluster of times. And here is again just a numerical experiment to show you that it's working. In most cases, as you see, it's not perfect, but it's working. We are able to recover a model which is very close to the best one. So best one is a yellow one. So in most cases, it's working. But when we miss the actual model, we are not very far away. And finally, it's not a big problem because we just would like to summarize the data. So it's not a big deal to have perhaps more cluster. So just coming back to the data to show you that it's interesting. So we use some data from 2009, 2020, so more than 10 years of data. And as you see, the dynamic of the data is very specific, in particular because in 2017-18, we have a huge peak of data, which is related to some, in fact, pharmacologic problems which were very well known, and in particular, thanks to the media, they have been very popular, unpopular, but and people report massively on the data, creating this kind of peak. And the problem is that, of course, this is related to a scandal for one drug, one specific drug, which was known. But at the same time, there was another very small scandal. And it was very difficult to see for the medical doctor because of this massive arrival of data. It was very difficult, and they almost miss it. So it was a problem at the moment. So here, in fact, it's related, so the big peaks are related to levothyrox and Mirena, which were very two problematic drugs at the moment. And when you cluster the data, thanks to our method, you recover something like this. So a first blue part, which is very low level of declaration, then something which is green, which is finally the normal level of declaration. And as you see here, in this period, we have a very complex analysis of the data, because we have this red part, which is almost anticipating the known scandal, then the scandal which is covered by the press, and afterward, this come back to the normal. And here, the purple part, which is related to the other drug, which was more difficult to detect. And we have this interaction matrix. So here you see for each cluster of drugs, the level of interaction with the adversarial effects. And this is, of course, not very easy for us to understand, but for medical doctors, it's very useful, because they can understand the change in the relationship between drugs and adversarial effects. And this was in particular the case of levothyrox, because levothyrox was the name of the drug, but the provider of the drug changed the formula. So the name was the same, but the formula was not the same. And in fact, you can see it here, because at some point it was headaches, etc. And another point it was heart attack. So it's not the same kind of adversarial effect. And here you can follow this kind of change. And it's very important for medical doctors to have this kind of vision of the interaction. And you can have also, so it's exactly the same data, but another representation, which is helpful for medical doctors to understand the dynamic of the adversarial effect for the different drugs. So this is a first work I wanted to present, and perhaps if I have 5 minutes, I can just very shortly propose you another work that we developed for clustering of networks. So it's partially related to the talk we had before, and here using also deep learning. So another specialty in my team is the analysis of networks. Could be social network, but could be also transportation network, whatever, protein-protein interaction network. And it's also interesting to do clustering to again summarize those massive data. If you think about social network, could be very large and difficult to follow. And for that, we propose some hybridization of deep learning and statistical learning. What we would like to use is to use the power of representation of deep learning, and in particular here it's graph neural networks, with the advantage and the theoretical guarantees that we have when we use statistical learning. So this is really what we wanted. So we have here the data that we would like to cluster. So this is just the adjacency matrix of the graph. We use a graph neural network to encode the data to go in some latent space. So we have Z, which is just a representation in a specific space of the nodes of the network. And here we start with statistical learning. So here we assume that now those observations belongs to clusters that are non-observed, and we are going to model those data in this space to be able to reconstruct something which is close to the data. So this is why also we have this decoder part. And thanks to this, we hope to have both the flexibility of neural network and the powerfulness of statistical learning. So just to detail you the generative model, as you will see, it's very close to what I presented before, because again, we have this C, which is the cluster membership of the data, which is again assumed to be a multinomial distribution of parameter pi. And then we assume that the latent position of the nodes, knowing that they belong to some clusters, are assumed to be Gaussian, okay, with a specific mean and a specific covariance matrix. And this is, when you do that, you assume a mixture of Gaussian in the latent space. And again, this part is quite easy. And after, to assume, after you have to infer it, and after you have to decode the latent position to reconstruct the data. And here we use some, again, statistical model, which is quite well known, which is the latent position model. You will assume that the connection between the node I and the node J, knowing that they belong to cluster K, cluster L, will be a Bernoulli distribution related to some encoding function of the latent position. And here the encoding function is proportional to the distance between the nodes. So the message is, if in the latent space two nodes are very close, they have a high priority to be connected in the network. If they are very far away, they have a low priority to be connected. So this, thanks to these assumptions, we should have some representation which is meaningful. This is what we would like to have. And again, after, it's the same story. Inferring this model from data is a nightmare. This is the lower bound that we would like to optimize. And we propose an algorithm which is, again, based partially on an EM algorithm, an expectation maximization algorithm, and gradient descent. So we have some parts which is that are done in PyTorch to optimize the loss, and some are explicit within this big iterative algorithm. And thanks to that, we were able to apply it to some original data coming from digital humanities. It's the analysis of a medieval network. In fact, it's a very old data because those data are dating to the 5th century. So it's a date, let's say, a Facebook of bishops in the 5th century in Gaul. And it's a very interesting network because it covers, in fact, more than 1 century and a half. And as you see here, here are the dates of the activity of people in the network. And you see a clear effect of the temporality, okay? Because, of course, at this period, people were living 40 years, perhaps 50. So it's very short activity. It was very difficult for this guy, of course, to be connected to this one because they lived 1 century ago. So it's very difficult. And thanks to that, thanks to our model, we were able to cluster the data to recover position in the network that are common, whatever the temporality. So it's interesting to see that this group of people were behaving in the same manner than this one, which is, in fact, in activity probably 50 or 60 years later. So it's interesting to recover this kind of behavior in the network. And of course, it's interesting because here it's a network of power. So it's a very interesting network by this time. So these are the two works, the summary of the two works I presented to you. You have also the publication if you would like to go see with them, perhaps. So this is just a very simple conclusion, which is coming from a French poet. Ce qui est simple est toujours faux, ce qui ne l'est pas est inutilisable. It's very interesting because it's very true to machine learning, statistical learning, because which is not simple is always wrong, which is complex is not possible to use. So it's interesting because it's the spirit of statistical machine learning. We are always in this trade-off of something complex enough to analyze complex problem, but not too complex because we are human and we cannot understand complex models. And you also can find some information in this book I published with some co-authors. And of course, again, we have some open position for at Institut Côte d'Azur for PhD student postdoc, but also for exchange of researchers. So of course, don't hesitate either to go here or to just write to us. Thank you very much. Yeah, perhaps it's better. Yeah. Your turn.
I will introduce you. I'll introduce you just a moment.
Could you please tell me when I have 5 minutes more?
Okay, okay. I'll introduce you. Yes. Serena will give a talk.
No. This
Okay,
way.
okay. Serena Villata. She's a research director at CNRS. She's chair in artificial intelligence and deputy scientific director of the Institut 3IA. 3IA. Ah, j'ai dit correct. Donc c'est bon. Merci pour.
Thank you. Thank you a lot. So today I will talk about argumentation and how it can be used to, in a way, help people to do some reasoning tasks. And of course, I will also highlight a number of issues because there are many open problems. So I will have just very few solutions and many problems that I will present. So what is argumentation? Argumentation is a reasoning framework that has been conceived with the aim to justify a decision, a position, an idea. And it's important to take decision, to convince the other about our viewpoints, and also to explain. And this is also kind of a keyword these days where explainable AI is central in AI research. So one important thing to highlight is that it's an interdisciplinary topic. So it's not just computer scientists doing that. So it's there is a lot of work around artificial intelligence about argumentation, but of course, philosophy, psychology, linguistics are all involved in this research area. And a number of concrete applications of this formal framework in the medical domain for evidence-based reasoning, for instance, to help doctors in taking diagnosis, argumentative diagnosis. In the legal domain, a lot of applications to explain the decision made by the judge through cases, examples, and previous decisions. And then, of course, with the web, there has been a rise of online debate platforms which claim to be argumentative. Some of them are, some of them are less. But anyway, this is other good examples. So in formal argumentation, what do we have? This is really, let's say, making a long story short, very short, is we start with the knowledge basis of different agents, let's say, okay, artificial agents. From this knowledge basis, which can be encoded in different kinds of logics, okay, I will not go too much into the details. We build the arguments, we identify what we call the attacks, okay, between these arguments. And then, of course, we can also identify supports, okay, so we can also have bipolar argumentation, but let's keep it very simple. And then, actually, what we are interested in doing is we have the argument, so we have this information, these pieces of information. We know that some of them are, let's say, there are inconsistencies if we put them all together. So we have these attacks that are identified, and we want to select what are the acceptable arguments. So we do that, we select the good arguments, and from these good arguments, we can raise some conclusion, which is sound. Okay, so that's the goal. And then at a certain point in this in the story, a bunch of people say, okay, that's very nice, but we always talk about argumentation. We always propose examples of argumentation, which are arguments in natural language, okay, real arguments that people use, because this is very natural. But are we actually able to extract these arguments from real text? So that was the challenge. Actually, in a way, we tackled this challenging task in 2012, more or less, to start with that, and we said, okay, let's try to have this new topic, which is called argument mining. We want to extract arguments automatically from text. So why 2012? Well, many reasons. So the first one, there are a number of large resources of natural language arguments that were becoming available on the web, like user-generated contents, product reviews, and so on, but also more legal text, more medical text, and so on. So it was a kind of a good moment to start with. And then, of course, also the advances in NLP and machine learning. So it was a kind of the right moment. In a way, argument mining is not opinion mining. If I have to summarize, for opinion mining, you are interested in knowing the opinion of people about, for instance, a certain product. In argument mining, you are interested in knowing why people has this opinion with respect to this product, which is different. At the beginning, we said we want to go through this argument mining. How do we tackle this task? The task has been defined at the beginning as a task of analyzing discourse on the pragmatics level and applying a certain argumentation theory, which means it could be a standard Dung model or a bipolar argumentation. It depends on the need of the application also, and automatically analyze the data. So we said, let's keep it simple. What we have when we have argumentation, if we represent an argumentation under the form of an argumentation graph, we have that the nodes are the pieces of information, are the arguments, and then we have these relations, which are the edges in the graph, okay? So let's start with that. We want to identify first the arguments, and then we want to predict the relations holding between these arguments. So we say we start with text. We have a first step, which is the argument component detection. To take, let's say, the task, let's say, the basic, we said, okay, we start by identifying evidence and claims, so the two main components of a basic argument structure. Then we predict the relations, which could be, for instance, support and attack relations. And then what we get as the output is annotated text. So here there is an example. We start with some text like this one, okay? Which is a text taken from a document. And then what we want is we want to move from this unstructured representation to the structured one, okay? Where we have that this is the claim, which is actually supported by some arguments and attacked by others, like in this example. So these are premises, okay, of the argument. This is the conclusion, and then we have support and attack relations with respect to the argument. So so far so good. This was the task we decided to tackle, and now I will show you some of the concrete examples we faced. So first we started with social networks, because in a way it's easy, the data is available, it seems to be easy to collect, and so we said we start with Twitter, and we decided to identify first the argument, so doing a binary classification, given a Twitter stream, identifying what are the, let's say, the argumentative tweets and those that are not argumentative. And then we said for those that are argumentative, we are interested in classifying them as being, let's say, opinionated arguments or factual arguments. And then we go into the sources, identifying the source. So just to point out an important distinction, we weren't doing any fact checking, okay? When I say factual, it doesn't mean true, okay? Never means true, okay? So it means just that is objective. There is not an opinion, it's not a sentiment in the sentence, which is very different. So We have taken as topics the Brexit and the Brexit. It was the right moment at the time. And we annotated a corpus, because this is a bit also of a problem in argument mining, because when we started as a community, there was no data, okay? No annotated data set to start with. And so everybody has built his own, okay? So this was the one we built. So we computed the inter-annotator agreement. It was okay. And we make these with these two topics on Twitter. And so an example of factual argument is this one: The Guardian, Greek crisis, European leaders scramble for response to referendum no vote. So in a way, there is not strong sentiment opinion in there. And we were interested also in identifying the source of the factual tweet when available. Of course, the source is not the account tweeting, because that's quite straightforward. It's if there is in the text the source of the sentence, of the argument. And then opinionated arguments, more like the second one: Trump is going to sell us back to England, Brexit, and so on. So we use a kind of standard methods, heuristic regression, and so on, with a number of standard features as well, and these were the results we get. Not bad. Going from these into a full argument mining pipeline, meaning identifying also the relations, was super difficult. And in a way, at a certain point, we stopped. So then we moved to another topic that was due to a project we had in the team. And the idea was to identify argumentative structures from text in clinical domain, okay? Because there are a number of works in argumentation about evidence-based reasoning. So we say it's very nice if we can provide the first step. First, we mine the knowledge, and then they have these arguments to do evidence-based reasoning. So the task was the full pipeline. So in this case, so first the argument component detection and classification, and then the relation prediction. So we also in this case, first step, building the corpus, okay? So collecting, annotating the corpus. For the medical domain, it's always a mess, okay? Because basically you are not allowed to access all the data, or if you have it, you cannot publish it. So that's a bit of a blocking point. So we said, okay, let's go to some data which is available, and we went to PubMed, and we have taken the abstracts of PubMed articles. We have selected these 5 topics, so neoplasm, which is a quite large topic, okay, because then there are many different cancer types here: glaucoma, hepatitis, diabetes, and hypertension. And we have taken only the abstract, okay? So that's what we have taken, and then we have annotated these, identifying the premises, like in this case in blue, and the conclusion, like the one in green. So all these is not automatically identified. I mean, there are no tags in the abstract, which simplifies the work in a way. So that's what we did. We use deep learning methods for doing so, and a language model which has been built especially for the medical domain. In this way, it was Shibert. Also, BioBert was performing quite well, but Shibert was doing better. And so these are the results we get, which we were pretty happy about it, in particular for the relation. Sorry, for the components. For the relation, it was okay, in line with the state of the art, outperforming a bit, but still, okay, as you may see, is not completely satisfiable. Because if you give this to doctors, they say, so what? That's really, this for you, this is working. So that's the bit of an issue. So this was just the architecture, but I will not go too much into the details because there is a lack of time. Anyway, we start with the randomized clinical trials, so the abstracts on PubMed. We identify the components. Once we have the components, we move to the relation classification, which is treated as a sequence tagging problem, and then we build the graph. Okay, so at the end, the outcome of all these is an argumentation graph. We also added some additional features, meaning for some of the effects, we identified automatically whether they were increasing or decreasing, because these are information that can be used by doctor. And we have an online demo which you can test, which is called ACTA, which exactly employs these arguments. So you can select automatically the articles you want to analyze on PubMed. There is an API connecting, and then you click on one. It shows you the argument graphs, and it highlights also these elements in the text of the abstract, so you can test it. And then we went to let's say, really the more natural scenario ever. So we said argumentation, debates, political debates, very natural. Okay, so let's go for that. Sounds easy. We were pretty happy about the results on the clinical domain. We said nothing can go wrong. We'll do that. Well, we started with the political debates in the US, the debates. All the presidential debates in the US, so it was a huge corpus. The nice thing is that the transcripts are all available, so that's a kind of the reason. So we collected all that, and our goal was to go towards fallacies detection. But first we said, let's identify the arguments, and then we will go to the most difficult part. So this is the data set we built. Okay, so that's we have all the candidates which participated. For each year, you have the type of debate. So here it was presidential. Here it was a presidential and the vice presidents. So it depends on the people participating. So from Nixon, Kennedy to Trump, Clinton. So now we have also the last one, but we didn't include it yet there. Number of speech turns, number of sentences, number of tokens. So it's quite a huge data set that we collected, and we annotated with argument components, so premise and claims, and support and attack relations. So just to let you know a bit how they look like, then here there are kind of nice short examples. Some of them are much more difficult. This has been a bit of a nightmare to annotate, okay? Because you need to take people knowing a bit about US politics. You need to take people which are not anyway biased too much in their annotation. So that's a difficult compromise to reach, okay? So it's complex. So here, for instance, an example where we have a conclusion and the premises. So for instance, Nixon says, I favor the present depletion allowance. So this is the claim. And then he explains why. I favor it not because I want to make a lot of oil men rich, but because I want to make America rich. And then it continues the explanation. So we had to identify all that, the argument components, but then the very difficult part was to identify the relations, because these debates are huge, okay? And so sometimes you have relations which spans from from argument components which are very far in the debate. That was a very complex, even for the annotation. I'm not even talking here about the system doing that alone. So that was the problem. Anyway, we built the corpus. The corpus is available online. So at the end, what we have is that we start with the text and we get the argument graphs. Okay, so that's what we have automatically. So here there is just a small examples. These argument graphs are huge. So in a way, that's also nice from the computational models of argument point of view to have these graphs, because those for Twitter or for the medical domain were just very small. So from the computational point of view, it was not, very interesting to compute, for instance, extensions and knowing what are the acceptable arguments. Here, it's a bit more interesting, I would say. So just to let you know a bit what are the results on this corpus. So for the components, we get, let's say, quite good results. For the relations, as you may see, is lower than for the clinical domain. So we are really working hard on that, improving. Still very, it's a difficult task. Anyway, that was a hit. We built the corpus. We have reasonable results for the whole pipeline, and there is also a demo, which is a Brasilia demo, which allows you to explore the data set, and so to navigate through the debates and look when there is what are the premises, the conclusions in all the debates you have, and you can identify name entities and so on. You can select the kind of debate you want, the participants, and that's a nice way also to explore, to do that exploration for that. And so we say, okay, we have the data set, we have no more excuses, so we need to go towards the end. We went to the detection of fallacies, okay, fallacious arguments. So this is a paper we got published this year at ICHCAI. Well, what are fallacious arguments? First, let's start with that. So here there are some examples. Nixon say, I would remind Senator Kennedy of the past 50 years. I would ask him to name one Republican president who led this nation into war. There were 3 Democratic presidents who led us into war. And then he says, I do not mean by that one party is a war party and the other party is a peace party, but I do say that any statement to the effect that the Republican Party is trigger happy is believed by the record. So this is a correlation that's causation fallacy, okay? Because there is a correlation, but of course there is not a causation link between the two. But the way it is let's say put forward in front of the audience, it's a bit misleading. So this is the goal of fallacious arguments. Again, it's not a matter of truth or false, okay? It's not a matter of that. It's not fact-checking, it's nothing like that. It's a way to convey an information in a way which is misleading, because the goal is to make the audience think something, okay? There is a communication message which has to be passed by. So ad hominem, here we have the usual suspect, so Trump, he says, certainly I'm not, he's talking about women and so on. Certainly I'm not proud of it, but that was something that happened. If you look at Bill Clinton, far worse, minor words, and his was action. His was what is done to women. Okay, so this is a very personal attack. That's what we call an ad hominem attack, fallacious arguments, because he's attacking the person, not the ideas, his arguments, his political viewpoint. And in addition, I mean, Bill Clinton was not in competition with him. I mean, it was his wife, so it's really an ad hominem attack. And then another kind of, let's say more, let's say positive fallacious argument, but still fallacious, okay? It doesn't mean that it's better, is an appeal to emotion. So Kerry says he met Michael J. Fox, the actor, and who's suffering from Parkinson. And then he said, this fellow stood up and he was quivering. His whole body was shaking from the nerve disease and muscular disease that he had. And he said to me and to the whole hall, he said, you know, don't take away my hope, because my hope is what keeps me going, and so on. And then he talks about Chris Reeves. So here he is really appealing to an empathic, let's say, feedback from the audience to then go into this kind of research in more in detail. So this is an appeal to emotion fallacies. So what did we do to identify all that? Well, first of all, we did a study to understand which were the main fallacies existing, because of course there were many, but some of them were just few instances in the data set, and so it was then not possible to anyway learn anything about that, at least not at the first stage, without injecting any knowledge. So we decided to, we did another annotation layer. So we have the basics, and then we have the argument components, relations, and then we have these ones. So we annotated these 6 types of fallacies. So ad hominem, appeal to emotion, appeal to authority, meaning something like I say that, so I mean kind of ethos, okay, arguments. Slippery slope, when something small happened and in a way you assign to these huge consequences about that. False cause, like the one you have seen, and then a slogan, so which is standard that we know from politics. So here there is just some, just to Google quickly, some, let's say, statistics on the data set. Interesting to know that most fallacies were in 2016. It's Trump-Clinton, if you want to know. And then a number of, here the distribution of the fallacies over the different data sets. So the approach was a multi-class classification of fallacies. So we relied a lot on language models, BERT, Roberta. And we used long-formal and transformer Excel as methods because the text is huge. I mean, it's a huge portion of text. This is the architecture anyway. Everything is on the paper. So what is important is that we have taken into account not only the fallacious text snippet, but also the context, because there are many important information which are around it, and also when there were arguments and when there were relations connecting these text snippet to the other. So these are the results we obtained. As you see, these are the results we have using long-former, which was the best model, without using argumentation features. So 61 is not that good. But if you use argument components and argument relations, it really improves. So it means that these information are in a way useful to identify these fallacious arguments. And here is the score we have for each of the different categories. And as you may see, some of them are more difficult to be identified than others. That's as expected. So just to conclude, that was a difficult task. It was difficult. And in a way, I think this task of identifying fallacious arguments makes it very, let's say, it really underlines the need of coupling knowledge and pure machine learning, because just using that it's not enough. And here also we have taken the 6 easiest, let's say, fallacious arguments, because fallacious arguments, there are kind of 65 different kinds of fallacious arguments, and some of them relies a lot more on the reasoning part. So that's an issue. So the importance of common sense knowledge is evident, in particular in this kind of domain. And then, of course, here we say this is an appeal to authority, but some of these fallacious arguments were actually over more fallacies. Okay, so what do we have a kind of a, let's say, a multi-class association, or more a fuzzy label of degree of belonging to this? Causal inference, difficult to assess it, and of course it would be nice to generate new arguments to counter the formal invalidity of these fallacious arguments. So in a way, explaining why it is fallacious and counter it with kind of correct arguments. And well, that's it. Thanks a lot. Renata, hi. Hi. Okay.
Okay, so thanks a lot for the talk. I was wondering, because we know that rational reasoning is completely different from human reasoning. So when you look at the health domain, it makes perfectly sense to find something logical there, because you want to give an explanation. But then, so the philosophers are studying what politics and I was wondering whether with all the data you have, we can come up with a new theory for argumentation that is not normative, but descriptive.
Yeah, that's a very, very interesting question. Yeah, kind of, let's say, seeing what is emerging from the data about the way they are debating. Yeah, definitely this is not rational, and it's very, when we think about argumentation in terms of critical thinking, and then you look at these debates, it's clear that there is a huge gap between the two things, and also I do agree. What we also identified, but definitely we need to have some more deep study on that, is also really the impact of emotions and so on, which is I don't want to say completely disregarded from the computational models of argument point of view, but almost in a way. Yeah, it's a very good point.
I have a question. So it's actually, I actually have some questions. So yeah, I have a question to Charles, but also to Terry. Come back. So,
Yeah.
So actually, let me start with the first section, where you describe the funding in the center. So I'm impressed that you have 140 companies. So I'm interested around. This is interesting. So I'm wondering whether all projects are run by faculty people, or you have like engineers or computer scientists around. So this is the first question. So maybe,
Yeah. So yeah, it's a good question, because in fact it was not so easy to manage indeed. So first, in the 140 companies that are putting a lot of money, or some that are just doing very short collaboration with the limited contract, but still. And indeed, we have this number, let's say 50 shareholders that are able to do something with the companies, but of course they are extremely solicited at the moment. And this is why we have created this tech pool of engineers that are really here to help the researcher to work on with the companies. So those engineers are here to have the first discussion with the company, to just see if it's really research or is just applying something that we have in the library, etc. And then if there is a research contract to engage, the researcher will be here, but probably the engineer will be doing the work under the supervision of the researcher. And at some point, of course, the researcher, or I don't know, a PhD student or a postdoc can also bring some theory inside. But yeah, we have this tech pool, which is really here to in between, to help this collaboration with this company, which is quite time demanding.
Oh, nice. So I have some technical questions, but let me just switch to Serena. Maybe we can talk during the coffee break. So Serena, I actually saw your presentation at NMR, and you showed the tool there, but you didn't talk about the underlying argumentation graph. So I'm wondering whether that graph is available. Can we actually access the graph or use the graph? And whether you tried or not to encode uncertainty in the arguments, whether you think this is important or not.
Yes, thanks. Two very good questions. So these graphs are available. So the graphs in particular about the political debates. These are the most interesting ones. We also worked on a debate platform a while ago. It was a Debatepedia. Now it's called iDebate. That graphs are available too, but let's say less interesting for us. For instance, something we found in these graphs is that there were no cycles. So in argumentation, I mean, we do like cycles. Okay, these are the issue from the theoretical point of view. Okay, because we have cycles, or the extensions and so on. In these real graphs, we don't have them. In the political ones, neither, but still it's much more complex, the graphs are. So it's more interesting also for the computation of the extensions. So yes, they are available. For uncertainty, that's a very good point. No, we don't assess it yet. We are working on assessing the quality of the arguments, and this could also lead then to assessing the uncertainty in the argument. At the moment, we are going into 3 standard labels, so the cogency, the reasonableness, and so on. But still, this is it's a very good question. Something to do.
Some questions for the chat. Can I pose a question? Yes. What is the person with report needed for labeling a corpus like the political debate
corpuses? Yes, thanks for the question. So it was a huge effort. I cannot quantify it in.
Hear the question?
Okay, I will read aloud. Can I pose a question? Where is the person week effort needed for labeling a corpus like the political debate corpus?
So for this corpus, it was I cannot quantify it in terms of a person week effort, but actually it was two expert annotators which annotated part of the corpus, established the guidelines, annotated part of the corpus, revised the guidelines, and then we had three annotators which were really annotating the whole corpus, and it took about 9 months to get the whole corpus, which is a lot. I cannot quantify in terms of. The point is that it's difficult. Now we are showing numbers of it doing it measure, but actually we should always keep in mind that there is a human upper bound. So how difficult is a task already for humans? It's not just for the system. It's very difficult.
So you treated both corpus as English corpus, okay? But is it the same language? You have a Psi word for science. Don't you have a Pol word for politics or something like that? I mean, wouldn't that be natural to try to build?
That's a very good point. Actually, there is not at the moment. Let me think what we are doing in the latest experiment. We are still using, I think Roberta is the best one for the moment for this kind of task, but definitely it would be interesting. Now they are really, let's say, spreading all these language models. We have SheBERT, the BioBERT, now we have also a legal BERT or something like that for legal language. Exactly. So that could be also a good point. Yeah.
Sharp, maybe I have a question. Sorry, that's long, technical question, but I'm wondering. I'll try to respond. I'm wondering, you used Gibbs sampling for the statistical model, and you used EM plus gradient descent for the neural. Did you try using differential methods for the purely statistical model or not, or you don't like that, or? Why did you change between that?
Yeah, it's a very good question. In fact, we are using very specific models that are mixture models, and we know from theory that EM algorithm is optimal for this kind of task. You really can try to use gradient descent for that, but the optimization will be clearly worse and longer. So it's very interesting. It's a specific case where this kind of algorithm is, so I'm not an expert in optimization, but EM algorithm is part of the algorithms, maximization, minimization algorithms, which are really optimal for this kind of task. So it's a specific task, and clearly here at the moment, EM algorithm is the most appropriate. And here we have a specific case where we have these two latent variables, and for that, it's prime for EM, and this is why within the step we have to do Gibbs sampling. So we still an EM algorithm, but just for the each step we approximate it with Gibbs sampling, which is of course it's model MCMC, so it's quite long, but yeah, it's working. And in the second model we use EM for the parameter of the mixture model, and the gradient descent is called within the EM step to optimize the parts related to the deep level.
So in both cases you have EM, but in one is EM plus Gibbs sampling, the other EM plus differential.
Exactly. The structure EM. For the first one, there is Gibbs within the E step, and for the second one, there is gradient descent in the M step. So it's a kind of, when you mix those kind of models, you also have to mix the algorithms that are devoted to the specific parts.
Thank you very much.
Thank you very much.
Just to say that tomorrow they will be available here in the afternoon, just to talk with people who are interested in knowing more about the troisième. Oui. Okay. Thank you. Thank you. Now we have a coffee. Now a special coffee.